Welcome to the second lecture in the series on structural analysis. In the previous one, we introduced some preliminary concepts on graphs, and now we're going to use them while introducing a description of a complex system that is called the components and services model. And this kind of description will be useful for formalizing some of the fault-tolerant approaches that we introduced before. In particular, approaches based on redundancy, physical redundancy, and online switching of failed components to backup components. So let us start. Let us explain better what is the motivation for structural analysis and for this model, this components and services model. As we anticipated, the first motivation is to organize knowledge about the structure of the system in a hierarchical way that allows then us to do some reasoning about how faults can affect the system and how fault tolerance can be enforced. This description is starting from a top level with a first node that represents our entire system. So these can be the spaceship or the tank or the HVAC. Every system can be represented as a collection of subsystems that concur to provide the functionality, so subsystem 1 of the entire system, subsystem 2, subsystem 3. All of them, we draw them connected to the system to represent the fact that they are each providing a subset of functionalities that are needed by the overall system. For example, these can be a system providing measurement. This can be a system including the actuators, and this can be a system where we have the controller. Subsystems themselves can be described as a collection of components. So let us describe, for instance, the subsystem 1 as a collection of component 1, component 2, and so on, component n. Furthermore, each component itself can provide one of a number of possible services. In the example where this subsystem is the measurement, the sensor subsystem, each one of these components can be a different sensor. So we have a temperature sensor, a pressure sensor, a velocity sensor, and so on. But the sensor can either be, I don't know, in standby, or can be in a modality where it is providing a very accurate measurement but consuming a lot of power, and another modality where it is providing a low value of the measurements, but it is also consuming low power, or can be in a modality where it is doing self-calibration. So we model that with a further expansion of these into lower level nodes. Each one is called a service. Service 1 up to service n. And finally, every single of these services can be described by some set of equations. So x dot equals some function of x and u, and y equals some other function of x and u. So the first motivation for drawing what Well, what you can see is a tree graph representing the structure of the system in terms of subsystems components is just to organize our knowledge. But the second is to check how faults can propagate. So let us assume that we have one component, so a temperature sensor, like in the spaceship example. And this component is not working, is not able to provide some intended service. And it is not even able to provide any of the other possible services. Then the entire component itself is not working, is failed. And if this happens, then this problem is going to propagate upwards to the subsystem level. So if the sensor subsystem has one sensor that is not working, then, well, there are several scenarios. One scenario that we had in the example with the spaceship was that the second component was actually a backup of the first. So if we are in this situation, a way to enforce fault tolerance would be to switch from this component to this one. We have a switch. And if we can do this, then the fault is contained. It is accommodated at this level. Its effects are not propagating forward up to the system level. But if this was not the case, so if we had no backup, then the fact that this was not working would cause the entire sensor subsystem to not provide its intended service, and this can cause the entire system to fail. Of course, you don't want this, and this is why you're organizing your subsystem and components in a way that you have a way to stop the propagation of a fault as soon as possible at lower levels. And one way, as we said, would be to switch to a backup, but also sometimes, if you don't have a backup, using what we said, the analytical redundancy relation, you can switch to a virtual version of the component that is not working. There are formal ways to do this analysis that now we just introduced it, and we will see them in the next lecture. They are called the fault tree analysis and the fault mode effects analysis. And now let's go a bit more into detail first of this model, the components and services model. As we introduced in the previous lecture, an example could be a smart building where you have several independent dwellings and each one has a heating subsystem, and this heating subsystem is comprised of several components, as for instance the boiler. And each component can have a number of services providing. The case of the boiler is to heat water, and this service is described by equations. Or we can also recall the tank example, where we have the controller, the wiring, the communication network, actuators, sensors, and the plant itself. So we can use actually this example as it is simple enough to introduce the formalism of the component and services model. So the first thing is that when we look at components, we are interested not so much the component itself, but from a system point of view, we are interested in the services it is providing. And in the case of the tank system, the service provided by the tank component is to store liquid. So what it is doing, it is integrating an inflow of liquid minus an outflow of liquid to get an amount of liquid stored. And the final product is that we have some level of liquid stored in the tank. In order to provide this service, the tank needs itself a vessel, and it needs input and output piping. So this seems trivial, but actually, if you don't have them, the tank is not holding any liquid, or you cannot put liquid in it. If your tank is healthy, so there are no holes in that, and if the pipes are connected, then the service will be provided. We don't need anything else. We don't need electric power. In a formal way, a service provided by a component is defined as a 6 tuple, that is an ordered list of 6 mathematical objects. So a service S is a tuple including a set of consumed variables, a set of produced variables, a set of processes, let's say physical phenomena happening in the components, then a set of request signals, a set of enable signal, and finally a set of resources. In the case of the tank, the consumed variables are the two flows, inflow and outflow. And what the tank is producing once it is consuming these variables is a level of stored liquid. The processes that are happening in the tank, so the physical phenomena happening, are described by this equation. The equation that tells us that the derivative of H is, assuming a unitary cross-section, is inflow minus outflow. And we also know that H is equal to the time integral of H dot plus some initial value H0. So this is what we described in the previous lecture when looking at bipartite graphs. Then we have a set of requests. So actually components can optionally provide a service. Sometimes they provide only when you ask them. So your smartphone is making a call only when you dial. But in the case of the tank, it is always providing the service, so you don't need to request it. It simply works like that. It's physics. And as well, the enable set is trivially always containing a single true variable. So the enable set refers to the fact that some components can operate only when some other conditions are matched. For instance, you have some systems that have safety features, and they will only operate if safety conditions are present. Or you can have, for instance, interlocking doors in a factory, and you can open one door only if the other door has been closed. This could be a kind of this situation. Finally, the set of resources for the tank comprise the vessel and the pipes. Okay, so hopefully this some way abstract definition is much clearer now that we consider this simple example. So as we said, this example is a bit trivial when we look at the set of request and enable conditions, because they are always true, but for more complex components, and especially components that need power and signals to operate, like the controller itself, then they are going to be less trivial. Anyway, services come in different versions. In the case of the tank, that was a simple case. There is only one way to provide the service. But if you have a component like a digital multimeter, for instance, the service it is providing, it is to measure currents or voltages. But they can be provided with different accuracy and different ranges. So if you turn this dial, you can select to measure currents that are small or currents that are big. You can measure voltages that are direct currents or alternating currents. So in general, a component is not, the behavior of a component is not uniquely determined, and what can provide can be different according to what you ask the component to do. Which kind of service a component can provide at any given time depends on which use mode the component is in. In the case of the digital multimeter, there is a one-to-one relation between the modality you select with the dial and the service provided. In the case of other components, the use mode can depend on some behavior that is encoded in the component. And to understand this, we can introduce this example, the one of the wireless speaker. So the wireless speaker can be in one of different use modes. It can be off, it can be disconnected, it can be in pairing with your device, your smartphone, or can be connected to your device. So if one of the service of the speaker is playing music, well, you can only play music if you are connected. So you can maybe already suspect that what we show here is related to one of the things we introduced in previous lectures, the finite state machine. Because indeed, the behavior of the wireless speaker can be described by a finite state machine. So you have each of the use modes represented by a state. So we have off, we have disconnected, we have pairing, and we have connected. From any of the other states, you can go back to off if you push the turn off button. These all represent pushing the off button. When you instead push the turn on button, the first thing is that you go into disconnected mode. If you push the pair button that you have on your speaker, you go into pairing. And if pairing is successful, you go to connected. This event-based behavior is exactly what finite state machines were born to describe. And components into this model are described using a state machine that tells you how you can switch from one use mode to another. At this point, we can introduce a formal model of a component. So a component is described by a finite state machine. And the finite state machine is described by a set of use modes from use mode 1 to some number, use mode n. So in the case of the wireless speaker, we had off, disconnected, pairing, and paired. And furthermore, we have a set of transitions. So the transitions were those Boolean function telling us when some input condition is present, then you can switch from one state to another. So the states are the use modes. Each use mode, in turn, include a set of services that can be provided, from service 1 up to service M. And finally, each service can be provided in different versions. So if you have a sensor, as we said, you can have measurements provided with high accuracy but consuming a lot of power, or provided with less accuracy but consuming less power, for example. So each service itself has a number of versions. Version 1 up to some version, let's say P. And finally, the versions are described using the 6th tuple we introduced it before. So the tuple of consumed variables, of produced variables, process, then requested, enable, and finally resources. Okay, this formal model allows us to do some reasoning, like we have one sensor that requires cooling water, because in order to make a measurement, the sensor needs to be cooled. So cooling water is one of the variables that are consumed by the sensor. But cooling water itself is produced by another component, a cooling system. So if the cooling system is failed, then no more cooling water is produced. And if there is no cooling water, then the consumed variable that was supposed to be available is no longer available. This means that we go back to here and we say, okay, this version of the service is no longer possible to be provided. It can be that this sensor is quite tolerant, and if cooling water is not present, still a measurement can be made, but maybe it is less accurate. So a fault-tolerant approach for the sensor will be to switch from the version that requires cooling water to the version that doesn't require it. And still, the service providing a measurement can be given. But if this is not the case, if cooling water indeed was required, then the service providing measurement is no longer available. And then, if that was the only service in the use mode, the normal use mode of the sensor, then the sensor will need to switch to another use mode. That could be, for instance, being offline. And if this happens, then we can have a cascade of events, because maybe this component is part of a subsystem, and if that subsystem is no longer able to provide this measurement, maybe this problem can also escalate further up in the hierarchy level. We are going, as we said, to show algorithms in order to do this propagation in the next lectures, but indeed the ability to do so is based first on the ability to model a system in a way like this one, as a hierarchy of subsystems, components, and services and use modes provided by the components. In the end, a component model can be formalized in this way. So we can have some formal definition of everything that we introduced so far in a graphical way. So a component is defined via a state transition graph. So the state transition graph is the one representing the finite state machine. We have a set of states, that is use modes. We have a set of transitions, tau, and we have some initial state, some initial use mode where we are. In the case of the wireless speaker, that is off. And each use mode, so each state of the finite state machine itself is a set of services, and these services, each one has a set of versions. And finally, every version is a six tuple where we have consumed, produced, variables, procedures, processes, requests, and enable conditions and resources. As we have shown today, this component and services model can be used to do some simple diagnosis, reasoning on the variables that are needed by each component and the variables that are provided by. On a more formal way, we're going to introduce in the next lecture how to use that for doing fault tree analysis and fault mode effect analysis. At the level of reasoning on fault tolerance, a component and services model allows to verify if in any possible condition where a component is failed, if we can switch to another component that is providing the same service such that the fault can be accommodated at the subsystem level. If this is not possible, then the fault is going to propagate up at system level. And so that was about the component and services model, and next lecture will be about FMEA and FTA, fault tree analysis.